inviting me. Always great pleasure to be here in Santa Barbara. So I'll tell you a little bit about a theoretical idea that was inspired by Long's experiments. In fact, we could have had this idea long ago without any experiments, but that's the great advantage of having these amazing experiments in the field. And I'll talk a little bit about whether this is actually relevant for the experiments he talked about. And before I get into the talk, these are all my collaborators, many of whom are actually here. So Junkai and Tomo, who are at Harvard, and Dan, who's now at UCSD, and we collaborated very closely with Mike Zaltel's group, Tiger and Tianle, who may actually, either one or both of them are here. And so there are two papers. I'll mention both of these in the talk. But I want to point out there are 3 other talks in this conference which are related, maybe more. So Yahweh and Santal and Dan. So this will be the one closest to this talk. I'll talk about part of this work, and I think Dan will talk about the rest of it. Okay, so we heard about these beautiful experiments of Long, where this fractional topological phases were seen in rhombohedral graphene. And this is the way we usually think about this. There is the integer topological band, and then you partially fill it, and you get the fractional topology. At least that's been the way this field has progressed. So in the 2 other cases where we have seen these fractional topological fractional Chern insulators, Xiaodong, today you heard more about these experiments. And before that, Amir looked at magic angle graphene, where these fractional phases were seen on applying a small field. Of course, in Xiaodong and Long's experiments, you didn't even need to apply this field. But in all of these previous 2 cases, we had a very good understanding of the integer state from which these descended. Okay, so the integer states actually required interactions because you have to polarize the spins or you have to polarize the valleys. You need some sort of ferromagnetism in order to create the integer state. But beyond that, the band topology comes from things that we understand fairly well, whether it's magic angle graphene, where many ways in which you can get Chern insulators, or in these Moiré TMDs, where again these integer phases were predicted before. Okay, so I think in some sense this is sort of the unique feature over here. One of the unique features is that it's not very obvious how you get this kind of band topology, even at the integer level, especially at the integer level, in order to get the parent state from which you could imagine getting these fractional states. Okay, so my entire talk will be actually focused on this question, just how you get these Chern integers, that part of this phase diagram, and I won't really talk about the fractions, and Dan may actually do that. Okay, so we already had a quick introduction to rhombohedral graphene. We are going to be looking in a strong displacement field. These are the relevant bands, the conduction and valence band, and we'll be partially filling the conduction band. Just to foreshadow what is coming, interactions will not just polarize the spin and valley, they'll also be important for creating the Chern bands. Yeah, and an extreme version of this is the idea that you already heard before, that in fact you have spontaneous breaking of translation symmetry, giving you these Chern bands. Okay, so just remind you of a case where we do have spontaneous breaking of translation symmetry, at least predicted for many decades now, is in the context of just a 2-dimensional electron gas with Coulomb interactions, just the simplest problem you could think of. And you have no imposed lattice, but the interactions between the electrons could spontaneously break translation symmetry and give you this Wigner crystal. And it's only recently, after many, many decades of work, that people have begun to see experimental evidence for the Wigner crystal. And this is something that's believed to, that you expect when you're in the limit of the potential energy really dominating over the kinetic energy. Okay, and there's a dimensionless number Rs that captures that competition. And the way you can argue for this state is you go to the limit where there's no kinetic energy at all. That's sort of the classical limit. Think of infinitely massive electrons. You minimize this to get a crystal, a triangular lattice of the electrons, and then you slowly turn on the kinetic energy. Okay, and when you do that, you can numerically try to establish a regime going from Rs equal to infinity down, and there's a finite range over which the state is stable, and that gives you establishes the stability of the Wigner crystal. Okay, there's a different way of thinking about this, which for my purposes is much more appropriate. If you like, this is sort of a wave picture of the Wigner crystal, where you think of filling bands that are self-consistently created by the potential itself. Okay, and in this point of view, you get bands, but of course the density at which you get a fully filled band can simply change if you change the density of electrons. Okay, so it's a self-consistent potential. You get band structure that is ends up giving you the insulator. Okay, so you can kind of make this a table where if you had an external potential giving you a band, this is the very well studied free electron problem. You could either get a trivial insulator or topological insulators like the Chern insulator. You can ask the analogous question when you have interactions between electrons giving you a crystal. From this self-consistent band point of view, you can think of the Wigner crystal as filling this box, but that leaves an open box over here, whether the interactions between electrons and something where there's no translation breaking, could they give you the analog of a Chern insulator? Okay, and of course, this question we could have asked long back, but somehow it has sort of evaded theoretical investigation, and we're going to call this state the anomalous Hall crystal. Okay, it's based on an earlier idea, the Hall crystal, which is somewhat different, where there is an applied magnetic field. So in a sense, you break translation symmetry, you break it down to magnetic translations. But here we are really thinking of a situation where there's no magnetic field applied, electrons in the continuum, if you like, effectively in the continuum, spontaneously crystallizing and giving you something which is the analog of a Chern insulator. Okay, so the thing that is, there are various consequences, but one of the first things that occurs if you have this analog is that the simple picture we had, this classical picture, where you start on this limit where you switch off the kinetic energy and then turn it back on to see the stability. This classical picture actually does not exist in this particular case. Okay, so you can go between band structures and this more real space picture when you have trivial bands and when there's a Vanier representation of the bands. But when you have Chern insulators, there is an obstruction to going freely between the band picture and this atomic picture. And this is really a consequence of topology. Okay, so if you wanted to make the same argument for this anomalous Hall crystal, start from a classical limit, you cannot really define that limit. Okay, so you're forced into this singular, sort of band or wave picture as the way to understand this. Okay, and so this goes back to questions about how, what actually makes a solid. So if you go back to this classic textbook, there is this idea, this conjecture that whenever you have a solid, you can really think of the particles in some limit as being classical. Okay, they're distinguishable, they're sort of classical, but in fact, if you have something like this anomalous Hall crystal, this intuition will not hold. So it's kind of interesting to think about the state for that, for those fundamental reasons, and also, things like you'll have a quantized Hall effect and so on. So there will be phenomena that are kind of unique to the system. Okay, but another question would be, where would you find it? What are the physical systems where this might occur? Okay, so that brings us to this n-layer rhombohedral graphene. Okay, so let me spend a couple of slides. We already have had an introduction to this and long talk, but let me spend a couple of slides reviewing the electronic structure of this rhombohedral graphene. Okay, so let's first start without any Moiré. We just have a stack, n-layer stack. Here's a 5-layer stack, and you apply the strong displacement field. And it turns out that the band structure that we flashed before has a rather simple interpretation. So you can think of rhombohedral graphene. Essentially, it's obtained by taking sheets of carbon and displacing them one on top of the other. And you can look at the tunneling paths for the electrons. If you keep the dominant tunnelings, so this is within each layer, and this is between the layers, it looks something like this. And if you look at the electronic structure close to the K point, so in the plane it's just V times K, that's just the linear Dirac node. So this is sort of a hybrid representation where in the plane, tunneling between A and B sublattices are written in momentum space, but from plane to plane, it's in real space. Okay, so you see that there is sort of an A to B, hopping, whether it's in plane or between the planes, at least in this dominant interactions, and then you wind up with essentially a 1D system. Okay, this looks like a 1D system once you reduce to momentum space in the plane, and this should remind you of a well-known 1D model, the SSH chain. And if this coupling, this V times K, is smaller than the coupling between the layers, the T1, you expect to get zero energy modes at the ends of this chain. Okay, and once you apply a displacement field, the zero energy modes will lift. They'll be moved to different energies. That's roughly set by the strength of this field. And that actually is the origin, essentially the origin of these bands you see. These live at opposite ends of the stack, of this n-layer stack. The reason they have any dispersion at all is because this is a finite stack, and the opposite ends can talk to each other, although in high order in perturbation theory, that ends up giving you a dispersion, but a very weak dispersion. And this is essentially the origin of these flat bands in this n-layer rhombohedral graphene. Okay, so it's been known that this is a good place to look for interesting topological phenomenon. Okay, but we're really going to be interested in this very large D field limit, where you have to sort of analyze the problem afresh. Okay, so the setup that Long was looking at is again the strong D field and a Moiré. So that is this Moiré at the HPN, which has a different lattice constant compared to graphene, ends up giving you a Moiré because of the lattice mismatch. Okay, so so if you put these two together, you can ask, what would I get? And again, we can go back to our standard approach, which is you think of the interactions as only polarizing the flavor and the spin degree of freedom. You have essentially non-interacting electrons once that ferromagnetism occurs. If I apply this Moiré potential on these non-interacting electrons, what do I get? Again, this is a strategy that has worked for us in the other cases. So you can try to do that. And what you find is that in this Moiré distant limit, where the electrons are on one end of the stack and the Moiré is at the opposite end, within this simple picture, you're really not able to get an isolated Moiré band. Again, you shouldn't be too surprised, because in this limit, the only way in which the Moiré is seen is through the tails of these edge modes reaching through the stack and looking at the other end of the system where the Moiré is present. Okay, so this is sort of in stark contrast to what is seen in the experiment. So in the experiment, when you go to the filling that matches the Moiré periodicity, that's this nu equal to 1, you see a very clear integer quantum Hall state, very good quantization of Rxy and Rxx that's going close to 0, and it's really this state that we are trying to understand what is going on over here. Okay, so in order to make progress with this, we need to add interactions in order to generate this churn band in this Moiré distant limit. Okay, so let's say you pick these parameters. You have to pick two things. One is the angle between the HPN and the graphene. This essentially tells you the period of the Moiré. And this is sort of a setup where even if you go to 0 Moiré angle, you still have some finite Moiré periodicity, unlike twisted bilayer graphene. So this is not really a singular limit. So this is a slow variation of the, a small variation of the period of the Moiré lattice. And this is the displacement field. It's important that we're in some strong displacement field limit. In our theory, this is it's roughly around 50. We can convert this, and this is roughly what we believe is where the experiments are parked. So let's sit in this at this point. This is what we get if we didn't include electron interactions beyond just polarization. But now we add that to our Moiré Hamiltonian and treat that within Hartree-Fock calculation. And then when you do that, you end up with this nice isolated Chern band. And of course, filling this Chern band will give you the what you expect or what is seen in the experiments. But here it was important to have interactions in order to create this Chern band. Okay, so this is sort of a new paradigm, if you like, for creating Chern bands, somewhat different from what we have seen, for example, in the twisted TMDs. Okay, so at this point, we were wondering whether this Moiré potential is actually required at all. It's really small to begin with. So what if, for example, we were to further weaken this Moiré potential? What would happen to this insulator, for example? What would happen to this gap for this Chern band? Yeah, so we did that in our calculations. So we have this potential strength, which is what is applied in our calculations to create this Moiré potential. So we weaken it, and you can look at the gaps. So these are the gaps that are plotted, and what you see is that as I turn off this Moiré potential, at least within our self-consistent Hartree-Fock calculations, the gap remains basically constant. It really doesn't care whether you put on this weak potential or not. And what this is telling us is that within the self-consistent sort of scheme, is that this is really spontaneous breaking of translation symmetry. Okay, so for example, if you were to do a similar calculation, say for a ferromagnet within Hartree-Fock theory, you could put in a magnetic field that is like breaking the symmetry by hand. You would get some gap, let's say, or some magnetization. As you turn off that applied field, you'd still have a finite residual gap or a finite residual magnetization. Okay, so that's really this method telling us that your system seems to be close to or in a spontaneous translation symmetry breaking state. And when you're in that limit, this is really this anomalous Hall crystal that we are talking about. Okay, so so we can go, once you identify that, you can ask a more, general question: where do you see the state in the phase diagram? Again, within this Hartree-Fock method, what are the parameters where you would expect to see this anomalous Hall crystal? Okay, and you have two things that you can tune. You can tune the density of electrons, and you can also tune this displacement field. So this I've plotted for some reason, as I'll explain in a little bit, with the square root of the density. And this is what the phase diagram looks like. So roughly speaking, if you go to large density, so what we're thinking about is you have, you prepare a system, maybe with a Moiré, but which essentially gives you an equal to one state with a large density. Or you can change that density and you can go down to very low density. You can scan this entire range. And what you find in this phase diagram, there are essentially three regimes in this large displacement field limit. At large densities, it's a metal. Shouldn't be surprised. That's exactly what happens for the Wigner crystal as well. You have to go to low densities in order to see the Wigner crystal. Here, it's fairly easy to see why large density would give you a metallic behavior. You have this very strong dispersion beyond a certain point, the certain point being the momentum at which this tunneling V times K is comparable to the interlayer coupling. And that density will be where this dispersion will begin to take off. So if your density is larger than that, you're up in this very dispersive part of the band and you expect to get metal. Okay, now if you go to very low densities, what happens? Well, actually what you expect is you get a crystal you get an insulator, but in that limit, you're just scanning such a small part of this Brillouin zone that you don't actually see any Berry curvature. Okay, so you're really down at this low density limit, and it will take you more momentum, more area of this momentum space in order to capture enough Berry curvature in order to see any kind of Chern physics. Okay, so in the limit of very small densities, the problem reduces to one of a low density electron gas in a band that does not have Berry curvature. It's the usual Wigner crystal problem, if you like, and you end up getting a Chern zero insulator within the self-consistent calculation. So those are the two extremes, the Wigner crystal on one side and the metal on the other side. Okay, and if you're in an intermediate density, that's where you expect to see this anomalous Hall crystal. Okay, so one thing worth pointing out is that this critical density we see over here, where this dispersion goes up, that's really where we said this V times K is of order the interlayer tunneling. In fact, a very similar combination of constants appears when you calculate the magic angle of graphene. Okay, so the densities corresponding to magic angle graphene, roughly speaking, is the density where you go from this metal to the insulator. Okay, but you'd also like to understand the phase boundary between the Chern 0 and the Chern 1 insulator, we know that you should be able to tune that as a function of density, and you also see it in this Hartree-Fock phase diagram. So what really sets that competition? Okay, so we had a very simple model that could kind of capture this tension between these two kinds of insulators, or the competition between these two kinds of insulators. We call it the three-patch model. And here what we do is, instead of doing a calculation keeping the entire Brillouin zone, we just focus on three momentum points in the Brillouin zone, the gamma and the 2K points. And so it's really kind of reducing this problem just to understanding what the electrons are doing at these 3 points. Okay, so so this competition you can kind of capture by focusing on this and asking how gaps open up, for example, at the K point. Okay, so before you put in a potential, if it's just a continuum system, there are 3 different plane waves that are present at this K point. There's this one and these two. These two are actually the same momentum as this if you had translation breaking. If you had a reciprocal lattice, you would be able to fold these onto this point. So there's a 3-fold degeneracy, and that is spontaneously lifted in the Hartree-Fock. You go from something that is gapless like that to something that's gapped. Okay, and the real question is, which linear combination of the 3 is selected? Okay, and depending on that, you get different Chern numbers. Okay, so that's kind of what we want to figure out. Interactions, we'll pick which linear combination and therefore which Chern number, and how does this vary as a function of the density. And so you can write down the Hartree-Fock, the energy from this Hartree-Fock calculation, but just restricting to these 3 points. In fact, for this particular calculation, you just restrict to 2 of them. And you find something that looks like this. So, so what are the terms over here? We're really trying to figure out what Chern number is picked up. Okay, and this tells you the energy function for getting different Chern numbers, different linear combinations. Okay, and so this, it turns out, depends on this angle, which is actually related to the overlap of wave functions at these 2 points in the Brillouin zone. Okay, so overlap of wave functions is very close to the Berry's phase, and through that to the Berry curvature that's enclosed inside the Brillouin zone. Okay, so in fact, this angle is roughly 1/3 of the Berry curvature, Berry flux in the Brillouin zone. Okay, so basically what this energy functional tells you is that depending on how much Berry flux I have in the Brillouin zone, if it's very small, I'd pick the Chern 0 state, and as this the Berry flux increases, at some point it becomes favorable to go from Chern 0 to Chern 1. And that's really what gives you this competition between the two insulators. And this just to remind you what the wave function looks like. We said it has this SSH kind of form. It's a surface state, so it kind of decays on going into the bulk. And the ratio between the amplitudes on the second layer to the first is this parameter eta. It's really the ratio of these two hoppings in plane and between the planes. And this is what ends up giving you these non-trivial overlaps of the wave function. Okay, so this eta is actually a complex number because the k I'm taking over here is really kx plus ik1. So the phase of this wave function, of this component of the wave function, changes from here to there, which is what gives you this non-trivial Berry's phase, or this non-trivial phase in the overlap. Okay, so you can see that this is essentially going to scale as the square root of density when I pick this k point as being on the boundary of the Brouwer zone. Okay, and what you find is that there is some particular density or particular eta where you switch from the low density say equal to 0 to the Chern 1 insulator within this analysis. Okay, and that's roughly where you enclose about pi Berry curvature within the Brouwer zone. Okay, and you can compare this to the Hartree-Fock phase diagram, and you see that you would expect some sort of phase boundary that is vertical. We have not really put the displacement field into this calculation, and this is slightly off from the true phase boundary. Maybe you would have put it down here. It's slightly off, but it's really good for such a simple kind of model. Okay, so this sort of quantifies how the Berry curvature in the Brouwer zone kind of seeds the final Chern number of this anomalous Hall crystal. Okay, so let me conclude. I talked about this idea of this anomalous Hall crystal. There are many more things one can say about it. For example, when does it show quantized Hall effect? You need to have either a Moiré or some disorder to pin it, and that's what leads to the quantization. One of the nice features that's more should be said about this, but we've run out of time, is that it will have gapless modes. It breaks a continuous symmetry, and so it has sound modes just like the Wigner crystal, but occurring on top of this topological crystal. And it seems to be very universal in terms of creating Chern bands. So you can add various details to this model, T2, T3, and so on. You can look at different numbers of layers. It very robustly ends up giving you these Chern insulators if the density and this displacement field are tuned into the right regime. And there have also been other very interesting models for the anomalous Hall crystal. Maybe we'll hear about them in this talk. So the ab initio modeling I talked about, there have been many improvements since our original work. People have looked at other ways in which the Moiré can be applied, or essentially is applied because of Coulomb effects. I think we'll hear more about ab initio in Dan's talk, or how the details of this Hartree-Fock. So one important thing to stress is that everything we did was self-consistent Hartree-Fock, which in the Wigner crystal problem is known to overestimate the width of this crystalline phase. Okay, in fact, by a large amount, by a factor of 30 in terms of this RS. Okay, so you might worry that something similar could happen over here, that we see this anomalous Hall crystal. Maybe we are seeing it even at interaction strengths that are much smaller than what a true theory. It's not very clear how you do this true theory in a reliable numerical way or a reliable theoretical way. But one thing I want to make, one point I want to make is that we do see this AHC. Sometimes there's a sweet spot, and there's a very large range of interaction strengths where the AHC is stabilized. Okay, and that will be an interesting program to really find in this vast parameter range that you have in rhombohedral devices. You have displacement field, different densities, you have different number of layers. Are there some sweet spots where you expect this AHC to be particularly stable? Okay, and also, what are the, are there new tools that we need new tools to really look beyond Hartree-Fock and study the stability of this picture. And one of the most obvious tools that you had for the Wigner crystal, kind of going to this classical limit is really not available for to you anymore. Okay, another question is about the experimental signatures. If you did have an AHC, let's say, somewhere else, some other part of parameter space, we see, quantization even in the absence of Moiré. How would you tell? That itself would be a huge, would be a very interesting finding. But maybe with the weak Moiré, would you see something like sliding conductivity? I think these are all still open questions. And maybe one of the most interesting questions you can ask, this is a way, spontaneous translation symmetry breaking to realize the integer state. But in principle, there's no reason why you could not realize a fractional state in the same way. Okay, so you create a Brillouin zone for yourself by spontaneous, translation symmetry breaking, so that the electron density is not at filling 1, but at filling 1/3. Okay, this of course would not open up a single particle gap, but in the second stage, you could imagine creating a Laughlin state, and thereby creating something that may be energetically favored. And again, are there models where we can study this in a reliable way and see if this kind of fractionalization in the continuum may be possible? Okay, so maybe I'll stop here.
Questions? Make my way back.
Thank you very much for these very nice results. So I have a question in this direction of beyond Hartree fog, because as you say, Hartree fog is biased toward showing ordered states, and how the question is, how robust do you expect these states to be? You are talking about this sweet spot. So do you really believe that there will be a spot there that will survive quantum fluctuations, dynamical fluctuations, whatever you can then include in your numerical and theoretical tools?
Yeah, so that's a great question. I don't have conclusive evidence, of course, partly because we don't have those kind of tools, right? That does not compromise system size on the one hand and keeps all quantum fluctuations in the model.
Would for instance, methods like variation or Monte Carlo help here, right?
Yeah.
Because this would be a way to go.
Yeah. So indeed, for the Wigner crystal problem, one of the references I had there was the work by Seppeli and collaborators, where they did variational Monte Carlo, and essentially they're starting kind of in the classical limit and allowing for these quantum fluctuations. Some point it melts, and I think the best estimate for RS comes from that. The complication over here is certainly worth trying those methods. Complication here is your broken time reversal symmetry. So your Monte Carlo will have not just the nodal sign structures, so which is, you can use fixed node, but it'll have complex phases. Now, I don't know how bad that is for Monte Carlo, but yeah, but I think this will really need some new tool development to,
Thank you. I'm a bit confused about the role that Moiré plays here, because in Long's paper, they do see fractional state at the fractional fillings of the Moiré and the integer filling of Moiré. So are you saying that it's a coincidence here?
Well, it's a little bit like if I gave you a ferromagnet in a magnetic field, right? Now, is it that that ferromagnet, you're seeing the magnetic moment because of the magnetic field, or because it's a ferromagnet? Right, it's really, it's hard to separate out those two things. So with the Moiré, depending on the strength of the Moiré, if there's an, underlying tendency for the electrons to form a crystal, and you put on a Moiré at exactly the right period, then you will, of course, get, the two will sort of
help enhance it.
Help, yeah, exactly. They will sort of act in concert. Now, if you were, the two things we could do is one, switch off the electron-electron interactions, at least in theory. And when we do that, when we completely switch it off, we don't see an insulating, Chern insulator. So the electron interactions are playing a role. The other thing you could do is remove the Moiré completely. In our self-consistent Hartree fog, we still see the crystal, but so far Long has not seen that. Now, is that because it's not there? Is it because the sample is somewhat disordered? We've not gone to low enough temperature, we've not picked the right parameter space, is not clear.
Okay, maybe one quick question, so what do you expect if you have a stronger Moiré? So that just kills it? or?
So one thing we did do is, we're trying to model the opposite side when the electrons are on the opposite side. So that's a particular kind of Moiré potential where you say there's a potential on the top layer of electrons, and you can crank up the strength. And if you do that, you make it very strong, you typically get a Chern zero insulator, but you could get a Chern insulator. But what we see is the Chern number you get is actually opposite to this one. So if you fix the valley and you apply a potential on just that top layer of electrons, usually you get Chern zero, sometimes you get Chern one, but it's the opposite sign.
Thank you.
Which is roughly, I want to say it's roughly what's in the experiment,
Yeah.
but there are some assumptions there. So.
Thank you.
A lot of questions, so I'm just going to make my way around.
Thank you, Ashvin, for the wonderful talk. I have one very naive question about the last point. So do you have any comments about how to realize the fractional anomalous Hall crystal by playing with the collective modes of fractional Hall?
What was the last part of the question?
We know the fractional Hall has a collective modes. Do you have any comments of realizing that by playing with that?
I haven't thought about that. How the collective modes appear in all of this.
I mean, the magneto.
Yeah.
Whether it's possible to realize that by, for example, let the collective modes close the gap at some momentum or something like that, in theory.
Okay, we should talk about it later. Yeah, I don't think I quite got the question.
Thanks for the nice talk, Ashvin. I have a couple of questions. So the first one is related to this anomalous Hall crystal. So it's a 2D system which breaks translation, continuous translation. So, and it seems like the Moiré is not important. So there must be something that's pinning it. Like, is there some idea about?
No, I would say the more, how much of a field do you need, right? For a ferromagnet, even a small field is good enough to align the magnetic moment.
Right, but then shouldn't it depend on the density, like in the Moiré unit cell? So it seems like it's seen over a continuous range of densities. Like,
Oh, you're talking about the extended.
Yeah. So,
okay, I didn't talk at all about the extended.
I see. So you're only talking about filling one.
Filling one, yes, Moiré. Yeah. Now you could speculate about the extended. That could it be there's an underlying Hall crystal that is somehow showing up. It has the right Hall conductance. But there actually you have a competition between the Moiré, what the Moiré wants to do, which is trying to get it has a periodicity equal to n equal to 1. And your actual density, which is what the crystal wants to do, which is a completely different period. So now the zero Moiré and the finite Moiré have completely different ground states, right? Zero Moiré would be, say, anomalous Hall crystal with density 1, and large Moiré would be anomalous Hall crystal, or something that where you only occupy the Moiré sites. So there it's a much more delicate question whether, switching off or switching it on, the Moiré is a much more delicate question because they kind of compete.
I see. Thanks. So another quick question, which is perhaps a bit technical. So it seems like the competition between the Chern 0 Wigner crystal and the Chern 1, like anomalous Hall crystal, depends on the distribution of the Berry curvature, which would depend very sensitively on the other T2 and T3 terms which you neglected. So is that, like, in spite of that, this phase remains robust?
I don't know if the distribution matters as much as how much is contained within the Brillouin zone.
Okay.
So that kind of showed up in the overlaps of the k-point wave functions. So of course, if you change the k-point wave functions significantly, then that could change. But we have redone the calculation with all these other. Actually, what I showed you was with all these other hoppings. Things change somewhat, but it's not that different.
Thanks.
Yeah, I'm trying to understand the AHC from an experimentalist point of view. So we know we know a lot about Wigner crystals. So in your vision, you're going from low RS to high RS. Low RS, you're in the quantum metal. High RS, you're going to Wigner crystal. and there's a small sliver of densities where you hit the AHC. So now we know very well how to detect the Wigner crystal. You can look in real space at a periodicity. You can look at STM. You can look at shear rigidity. You do that with RF spectroscopy. You can look at transport, look at pinning, and you see. Now, which one of these can I use to look at an AHC, and how am I going to know that this is what I have?
Yeah, so I think all of them would reveal some aspect of AHC. So a lot of the physics of AHC is like the Wigner crystal. So it will spontaneously break the translation symmetry. So, STM would be really perfect. Even when a lot of the evidence for Wigner crystal now is actually coming from scanning studies. STM would show broken translation symmetry. Now, of course, for this, you can ask, is there a difference? If I just look at the picture, can I tell this is AHC versus Wigner crystal? I think in general, you cannot do that. But in this particular case, if you look at the charge densities we get in the two parts of the phase diagram, churn 0 and churn 1, they actually look quite different. So in the Wigner crystal, it looks like a triangular lattice. So the charge is peaked on the triangular lattice sides, whereas in this AHC, the density is peaked on the honeycomb lattice sides. There's no perfect C2 symmetry, of course. Everything is low symmetry, so the A and B are different. But so for this particular system, I would say look for charge density peaks, and what is the pattern? Is it more like honeycomb lattice versus triangular lattice? But the universal thing about the AHC is that if it is pinned, it will give you a Hall conductance. So everything else is like the Wigner crystal except for this part. So you will have edge modes, for example, which you could try to visualize in STM. I think these kind of questions are really important if you
So will it have shear rigidity, and does it get pinned just like a Wigner crystal?
Yeah.
Okay.
It's a solid, but it has this one weird property. It's got this edge state. So.
Okay, thank you.
Very nice talk. So I have a question about the phase diagram, because as I asked Long, there's at nu equals 1, there's the transition between a metal, a churn 0, a churn 1, and then a metal. As you argued from the patch model, which I have also a question about, but we'll get back to that. At nu equals 1, you're basically, from the patch model, guaranteed to get C equals 1, as you see in the phase diagram. So there's no churn 0. So do you see that as feature, problem? What's your take on that?
So you mean at low? Are you talking about low?
No, nu equals 1.
So nu equal to 1 depends on what density you pick. What is the Moiré periodicity? So I have not converted this to density. That depends on some ab initio parameters. But
at Long's density, right? He says he has a density in his.
Yeah. So to convert this to density, you need something like to know what T0 is. But if I'm allowed to pick a line, take this line over here. Is this what you want? You want anomalous Hall crystal or churn 1? You go down, you get churn 0. Above is metal. I mean,
but that's the density in the experiment at nu equals 1. I'm very confused.
So
it's not.
Well, it depends on how you convert this to density, right? So actually, there are two different, depending on whom you ask, ab initio parameters can be different. So the ones we used, I think, were out here for the experiment. But I think if you take other parameters, they're further out, or the modeling of these systems, I think, is still evolving. If I don't get the exact sequence as seen in experiment, I would put it down to modeling rather than the whole idea being wrong.
You think it's an issue of parameters?
Yeah.
Okay. And the second question was, so this 3-patch model, there's obviously a gapless line along Km.
Yeah.
Also, which can open.
Yes.
So your churn number is actually mod 3.
Yes, exactly. Yeah.
So you don't. So basically, you're neglecting the gapless line around gamma m, which can open and give you other churn numbers also. Like
yes,
like your churn number 1 can be 4.
Yes.
Okay.
Yeah. So this patch model alone does not tell you. If this was all we had, you'd have to take it with a big grain of salt. But it's really trying to understand this phase diagram. where we know the Chern numbers. And then in this regime, if you get something that is 1 mod 3, of course, you could insist it could be 4, but it's more likely just going to be what's seen in the Hartree-Fock.
I noticed one outliers in this phase diagram, that little red square that's connected from everything else. What's that? Why is that?
Yeah, so what we plotted over here, so maybe I should have explained this. So these shaded dots are where we see a metal in Hartree-Fock. Where we have squares but not shaded is where we have a Chern 1, but the gap is small. So, the robust part of the phase diagram is where the gap is, this is of order 20 MeV. Similarly for the circles, Chern 0, but they're not shaded, as the gap is small. But here sort of the gap recovers, right? But there is seems to be something protruding out here where the Chern 1 protrudes out in a region which is otherwise Chern 0.
Okay, I have to go further in the phase diagram to search for it.
Yeah, I mean, I don't know how much I'd bet on these, the small peninsulas and islands in the geography, but I think this trend with density is really, that's what I tried to explain.
Ashvin, so regarding the role of the Moiré or not, is there any chance of seeing something like the Goldstone modes to see that it's spontaneously symmetry broken? Can you comment on how can we see those?
Well, yeah, so they would be gapped if you had a Moiré. So it's like looking for spin waves in a magnetic field, but the hope would be the gap is small if the Moiré is weak. And maybe you can excite them in Raman or, we heard about RF spectroscopy. Of course, then you'd have to argue that they're really descendants of the Goldstone mode and not some interband excitation, which they will evolve into as the Moiré gets stronger, right? But maybe there are features that make it look more like Goldstone modes, selection rules and things like that. That could be one way to make the case, yeah. And Shankar had a question before, but... No, I want to hear the question, yeah.
Senthil is laughing, I'm sure. But your talk was so clear that I understood everything, which is not that frequent for me.
That's one reason why people don't ask questions. Right. But yeah.
But I have one informational question and then somewhat more technical. You kept on saying that, I think I misunderstood, kept on saying that Wigner crystal is stable over 30 to 40. That's just completely wrong.
Say it again, I couldn't hear you.
You kept on saying that Wigner crystal is stable, numeric show, between RS 30 to 40.
30 to infinity.
Infinity, right.
Yeah.
30 to 40 is the number.
30 to 40, somewhere there to infinity.
Yeah, every 5 years the number changes between 30 to 40, so that people who are doing the calculation can publish one more Kisrer letter. But it's some number between 30 to 40, and the best calculations are diffusion Monte Carlo, not. But the problem is that around that RS, you now have to worry about TC, because there's a classical TC for this problem. Because, the only Wigner crystal that has been definitively seen is by Mike Grimes, which is a classical Wigner crystal on helium. There you have to worry about gamma parameter. If you actually calculate TC by any approximation, it's of course going to be 0 close to this 30, and it'll go up, then it'll come down. So the thing is that it's a bit, even within Hartree-Fock, it's a bit tricky just to talk about Wigner crystal and the ground state problem, because Long's original experiment has 300 millikelvin. I kind of estimated it. TC seems to be around 100 millikelvin. We posted a paper tonight. All I'm saying is one story, but these are extremely demanding numerical questions.
Yes.
But we have to ask these questions. If TC turns out to be 1 millikelvin, then even if our idea, let's say we know, it's definitely, your idea is beautiful, it's not going to apply. So we have to take that next step in some sense, Second thing is that you touched upon it, so I want to be very, very nice and kind, is that, as you know, that this Hartree-Fock theory will say sodium is a charge density wave. And Al Overhauser, I think, believed it all his life, that sodium is not an electron, it's a charge density Wigner crystal. So this number question is of some importance here.
Yeah.
And as a community, I think we should try to do something better, some diffusion Monte Carlo, not variational, to see what it is. Okay. Do you agree with this, right?
Yeah. But for me, seeing the fact that it works out in self-consistent Hartree-Fock that's the first step. Right. It may not
absolutely.
It may not even have worked out in self-consistent.
No, absolutely. But the last question is that you are doing all of this, you're trying to understand the experiment. In the experiment, to the extent there is an insulating phase, that is consistent completely with the Anderson insulator rather than a Pin-Wigner solid, because
so you're talking the low density.
Yeah, low density, that's where, and this is of course an old question in quantum Hall also. What is the phase at, let's say, nu is equal to 1/7, where you go from fractional quantum Hall to a mega ohm insulator? I keep on believing in the Anderson insulator, but and that again is something one needs to worry about. Is it more an Anderson insulator or more a Pin-Wigner crystal? The difference is semantics.
Exactly, yeah. So I think, having, just like Long mentioned, having some scanning, probe information, even for the low density, it will be random, yeah. And also people see Wigner crystals in scanning probe when they would not see it in transport. So if it's there, maybe it's small patches, a scanning probe would show up. Yeah.
One last quick question, and we'll break for coffee.
My quick question would be, do you have any idea about whether a magnetic field would stabilize this even more? Whether there'd be some interesting competition between a possible Hall crystal and the anomalous Hall crystal?
Yeah, that's a good question. Of course, this is all broken time reversal symmetry, so on and so forth. So feels like a magnetic field would be good. Of course, it introduces another length scale. Question is, how does that length scale play with this one? We have not analyzed that, but that's a great idea, yeah. Try to analyze how, is it more stable in the field? Yeah.
Great. Thank you again.